Welcome to homework.
All right. This is a pretty difficult one. So we got a expression to compute the wave function as an integral in the variable k involving this coefficient b of k defined as this decaying exponential. We're first asked to find the omega k, also known as the half width, in which the b of omega k is half of its maximum value. We're then asked to, by any means necessary, compute psi of x, computing this integral. And I have to tell you, easy one to compute. I had to do a lot of searching to find a table that gave something that was actually doable. They recommend you do it by table, but it's not actually. I found it was not actually that easy to find the table, to find one with this very specific integral. But it can be done. Once we find psi of x, or what we think is psi of x, we can find the half width in real space as well, defined as psi of omega x is simply half of its maximum value. Once we have these, we can then take the half max in momentum, multiply it by the half max in space, and comment on the result. So let's start this up. Okay, so if b of k is defined as e to the negative a squared k squared, and we're asked to find a half max. So b of omega k is simply half of b of 0. It's going to simply be equal to half. Thus, 1 half equals e to the negative a squared omega k squared. You can take a natural log, isolate omega k. We find that it's equal to the square root of the negative natural log of 1 half over a squared. And we can make that a little bit nicer by having only a natural log in the top in the numerator. Done. Okay, so that's our omega k. Now, onto this integral. The only integral table I could find that gave us something that was actually useful to work with is this integral. And notice the bounds are slightly different. However, the function is symmetric, so we can simply cut it in half. That's not really a big issue. So the integral table that I found that might be useful for this problem is one of this form. This is a Gaussian integral of some kind. And it's equal to an exponential. We got to be very careful because these a's and sigmas are not, and x's are not the same. So if we let x be equal to k, if we let 1 over 2 sigma squared be our a squared, we move some stuff around. Oh, this is also the consequence of that is that sigma is root 2a. We can start working with this. So I'll try to squeeze it into one line and squeeze as much as I can. We can set this up that 2 times this integral of the exponent negative a squared k squared sine of kx dx is going to be equal to, I'm going to need to move some of this stuff here to the other side because it doesn't really belong, as you can see. Fortunately, they're constant, so I can pull them out of the integral and not worry about them. Root 2 pi, root 2 times a, the exponent of negative, so sigma squared is negative 2a squared, or this is now analogous to x squared, right? See what I mean? The variable names in the table are not very useful, not very helpful to us, rather. So we have to be very careful about this. Okay. So now I'm pretty confident that this integral that we actually want, e to the negative a squared x squared cosine of kx, of a squared k squared. See, once again, mixing out the x's and k's, dk will be equal to root pi times a times the exponent e to the negative a squared x squared. And I think that is our psi of x. Difficult to do, but it's possible. So when is this half max? This looks a lot like the previous one. It's to get a half max, we need to get something that looks like this. Oh, missing one thing. It would be, its maximum is root pi over a, root pi times a. We want half of that. So then we're looking for this, negative a squared. The x we're trying to look for is our omega x. So we can do essentially the same thing we did in part A, take a natural log. We're actually going to get the same result. That omega x is going to be the negative, the square root of the negative natural log of 1/2 over a. So it's identical. So the last thing we have to do is compute the product omega p omega x, I believe, yes. And omega p is defined as h over 2 pi omega k, which you already found in part A. And it's the same as omega x. So we're just going to end up with a square root's gone. We're 1/2. Got our a squared. And I believe that's it. And notice this doesn't depend at all on our variables, x's or k's or anything. It's a constant. And I think this is the point that we can interpret these omega p and omega x, these widths, as uncertainties in momentum and position space in the same way that we do delta x's and delta p's. So this product has to be equal to a constant. It can't depend on other things. So I think that's the idea. Really, really difficult problem. That integral is not easy, but that's it. These are the main results, I believe.